All right, good morning, gang. Welcome back. I'm glad to see everybody survived exam one. We're all still here. We're all still breathing. It's good. It's good. Today, I'm not going to hit you with too much, but I don't want to do nothing either. So the plan for today is to introduce a little bit some of the things we're going to be talking about in the next few weeks, and to try and show you a few examples of some cool techniques that we'll be encountering early next week to differentiate functions. Particularly, I want to talk about implicit differentiation. So let's do that. I'm going to turn on my doc cam here and then screen share. I can tell you a little bit about the test too as we get moving into it. So don't pay attention to the statistics on Canvas. I haven't graded the free response questions yet. So whatever, that candlestick chart that shows your score and the average or whatever, that's all going to change quite a bit. Nala, Nova. Sorry, my cats are fighting. Nova! Sorry, one second. Kitty cat. What the fuck are you doing? Why are you being a dick to your sister? Why are you fighting back? Come on, just come out here. Come on. No, kitty. All right, ever since we moved, my normally very timid male cat has decided he wants to beat up on our female cat all the time. But she's good, don't worry. All right, so we were talking about exam score stuff. Today's the 12th, right? Pretty sure it's the 12th. Okay, so some announcements. Here's the way I do things. Test one, exam one will be scored no later than next Wednesday. If I can get it done sooner than that, that's awesome. You'll see the score in there, but my promise to you is 1 week, always within 1 week. So within 1 week, you'll see accurate stats on Canvas, including your own. What else are we gonna say? Later than next week. We will begin chapter 4, which is going to involve implicit differentiation. I think something called related rates. Min-max problems. And some other stuff. The things to really watch out for, related rates, this is a tricky section. People tend to have a hard time with that for a few reasons, I think. First off, they're all word problems, right? Related rates is all about taking a physical situation, sometimes not necessarily physical, but a geometric situation, often a physical one, and kind of transposing it into a mathematics situation. So you take some formula and you differentiate on both sides with respect to time. And then you'll try to figure out, when this balloon is shrinking, how much air is flying out, that sort of shit. Implicit differentiation, less tricky. We're going to talk about that today. Min-max problems, this is actually, I think, section 4.1. And these are not too hard, but they're hugely important, finding local minima and local maxima. So next week, we're going to start chapter 4, which is all about applications of the derivative, kind of fun things you can do now that your differentiation skills are getting solid. And then next Wednesday, I'll have your exams back. I'm trying to think if there's any other announcements right now. There's no homework due on Monday. No new homework due Monday. So please take this time to catch up on any old stuff. right? If you didn't quite finish homework 3 or something, now's a really good time to submit an extension request and get that knocked out. Because you don't have anything new that's due on Monday. There's no fresh stuff for this week. So I'm not going to assign you anything new until next Monday. Then I'll give you something new. It'll be due the following Monday. We'll get back onto our regular schedule. But between now and Monday, nothing new. So let's do this. Let's do a little intro to implicit differentiation. And I'd like to talk a bit about something called the inverse function theorem. The inverse function theorem is not an official part of this course, but it's one of the most important theorems in analysis. Analysis is like big boy calculus. So yeah, inverse function theorem is kind of what underpins a lot of what we're going to do in implicit differentiation. Implicit differentiation is what it sounds like. I should say there's also something called, we're being cheeky here, but I'll say it, called the implicit function theorem. All of these things are intimately connected to each other. Here's the big idea. Maybe I have some curve and it's not actually a function, right? Maybe I've got something that looks like this. You know that since this thing massively fails, and I don't really care what it does, it could do, whatever it wants outside of here. This thing fails the horizontal line test, right? Like there are many horizontal lines that intersect this graph more than once. And there are many vertical lines that intersect this graph more than once. So because there are vertical lines that intersect this graph more than once, this is not a function. And because there are horizontal lines that intersect this graph more than once, its inverse is not a function. So there's no sort of way of thinking about this, whether I look at it like this or like this, where I can say this thing is a function. Right, this does not represent y as a function of x, nor does it represent x as a function of y. But if you look locally, if instead of looking at the whole thing all at once, if I just look, for example, in this little window here, within this little window, it does pass the vertical line test and it does pass the horizontal line test. So it is a function here and it is one-to-one. We can even talk about an inverse, and that's the big idea. So I would like to say that since this curve is smooth, I can still find a tangent line, right? This thing doesn't have any jagged edges on it. So I should still be able to talk about what the slope of the tangent line is at any point. And I'd like to say again that since this function, at least locally, is one-to-one, I can find an inverse, and that's the inverse function theorem. So, big idea. I'll write some words here. Even though this curve fails the vertical line test, not a function. And the horizontal line test which normally would mean not invertible, if we look at any small piece, that piece is a function, right? Passes the vertical line test and is invertible. Passes passes the horizontal line test. So we can still, the word is locally act like it's a function. It's a one-to-one function even. Okay, and I put piece there in orange because I'm going to come in here and say, hey, just look at this piece. I guess if we look at that piece as a whole, it's not one-to-one, but all right, if we just look at one tiny piece at a time, if I just look at that piece, or if I just look at this piece, right? If I kind of pay attention just to what's inside the little window, if I pretend like everything else isn't there, then this definitely does pass the vertical line test. If I just look at this piece, this passes both the vertical and horizontal line tests. If we look at any small piece, then that piece is a function, passes VLT, and is invertible, passes HLT. So VLT is vertical line test, HLT is horizontal line test. Right, like I should be able to get in here and talk about the slope of a tangent line, no problem. Clearly there is a reasonable slope of a tangent line here. It's not like the graph is so janky that I can't talk about a tangent line. But the question is, how do you do it?
Wait, doesn't that not pass the horizontal test as well?
So this little window here passes the vertical line test, but not the horizontal line test. This little window passes both. And if I were to shrink this window down to like this size, then it would also pass both. So kind of the big idea is if you use a small enough window, you can pass both the horizontal and vertical line tests for pretty much any curve. If you look locally, if you just look at a very, very small patch of it, then that little patch will be both one-to-one and a function. Right? You're right that this whole window, as I drew it here, isn't one-to-one. It is a function. It does pass the vertical line test, but this little bit here fails the horizontal line test. But if I were to shrink it down a little bit more to like just have this, that would pass both. Or if I were to just look at this, that would pass both. So this window right here definitely passes the vertical line test. And if I shrink it down a little bit more, I could get it to pass both. This little window right here definitely passes both. So the kind of question becomes, what sort of stuff can you have in your window and still allow for both of those things? Still allow you to locally be a function. Sorry, where are we? Implicit function theorem. Locally be a function and also locally be invertible. And that's what these two theorems give us. The inverse function theorem tells us exactly when we can kind of zoom in and get a one-to-one piece. And the implicit function theorem tells us exactly when we can zoom in and get a piece that passes the vertical line test. Now, you guys aren't going to be responsible for the hypotheses of those theorems. They're fairly complicated. Spelled implicit wrong. So yeah, generally these sort of examples are a little bit easier to understand than the broad definitions. But the basic idea is that if you zoom in on the graph of any nice smooth relation, then locally, if you zoom in enough, locally, you will find something that is both one-to-one and a function. That's the main concept there. And then another little piece of the implicit function theorem says if the whole curve is smooth, then when you zoom in, the piece you're looking at will also be smooth. So that implicit function, that function that you maybe don't have a formula for, but you know, like locally, this thing is definitely a function, is differentiable. So let me show you a concrete example here, and I think that'll make this a little bit easier to understand. Is anybody still writing here, or do we want to talk any more about this kind of big idea stuff? Okay. So the challenge here is that no curve like that can be expressed like y equals f of x, because it's definitely not a function. So let's look at a circle, the unit circle even. His equation is y squared plus x squared equals 1. Modulo my bad art, that's a circle. All right. Fails the vertical line test, fails the horizontal line test, is definitely neither one-to-one, nor is it a function. So how would you go about finding the tangent line if I asked you to? You know, one of the points we know is on here is like root 2 over 2, comma, root 2 over 2. How could we find this tangent line?
Could you just do sine over cosine?
Well, so you're getting at something neat there. The definition of tangent is related to the tangent function, right? Like the concept of a tangent line is related to the concept of a tangent function, but that tangent function actually tells you where the tangent line hits the x-axis. It doesn't tell you the slope of this line. It tells you where this line is going to hit over here. We could finagle that into this, but the question is, using the skills that we've talked about in this class, using differentiation, is there a way to find this tangent line? Normally, we'd say, like, differentiate f of x to get f primed of x, then plug, you know, whatever this x value is here, I'll call it a, into f primed of x for the slope. Why doesn't that work here?
We don't have an equation.
Yeah, we don't have f of x, right? I mean, we have an equation, but we don't have a function. So what the implicit function theorem does is it guarantees that you can look at this little piece here and say, oh yeah, this little piece on its own definitely is a function. And then whatever sort of tricks you can use to get your derivative to show up are acceptable. So what sort of tricks could we use to get the derivative we need here? Well, remember, if y is equal to f of x, then dy dx is the same as f primed of x, right? So let me just pretend that locally here, I do have some function. Right? I'll say that y is implicitly a function of x in here. Then I can differentiate everywhere through this expression using the chain rule. call this, and I'll call this equation up here star, and differentiate the equation star using the chain rule. Using the chain rule with respect to x. What I mean by that is I'm going to apply the operator d dx to both sides. So I take this equation and I slap a d dx on both sides. This is called implicit differentiation. We are differentiating with the implicit assumption that y is a function of x, or we are differentiating with the assumption that y is implicitly a function of x. That's where the term implicit differentiation comes from. Everybody with me so far? So I take this equation and I put d dx on both sides. d dx of 1 is 0, right? You differentiate a constant, you get 0. d dx of x squared is 2x. d dx of y squared, remember, we're thinking that y is implicitly a function of x. So this would be 2y times dy dx. The idea is if y is f of x, then I've got an outer and an inner. I'll put the explanation over here. d dx of y squared is like d dx of f of x all squared, which by the chain rule should be 2 times f of x times f primed of x, which is 2y, f of x is y, times f primed is dy dx. Okay, this is called implicit differentiation, and it's a really useful trick. So the y squared, you kind of differentiate the outside, like x squared becomes 2x, y squared becomes 2y. But then by the chain rule, you have to multiply by the derivative of the inner function. Well, the inner function is y. So the derivative of the inner function is dy dx. Some people just like to write this as y prime.
Why didn't you do that with the x squared?
You can, but dx is 1. That's a great question. So what happens if I do that here? If I have 2x times dx dx, right? Differentiating this thing with respect to this variable, where the thing here would be x. Dx dx, though, is just 1. If you take the derivative of x with respect to x, you can think of that as being here. It just happens to have value 1. Oh shit, this is running out of alternate colors. You can do this here too, right? Yeah, this would be 2x times dx dx. It's just that dx dx is equal to 1. It's because we're differentiating with respect to the variable x. Because the particular operator I applied was d dx, meaning differentiate this thing with respect to the variable x, that the kind of chain rule part you would get from differentiating x squared would be d, well, whatever you're differentiating, which is x over dx. And that notation really is just 1. Dx dx is 1. So this is another question we could have asked at the time of the chain rule too, right? Like, when do you stop with the chain rule? That's something that people often ask when they're learning it. Like, I can keep peeling off layers and differentiating one layer deeper and one layer deeper. How do I know when to stop? Well, when you get down to the derivative of your variable with respect to your variable, right? When you get down to something that looks like this, that's when you know to stop, because that's not, there is nothing deeper, right? You're not actually digging down any further. You just get a 1 here. Does that make sense? Maybe a little bit of sense? Okay. So the y squared becomes 2y times dy dx. The x squared becomes 2x. And you can think of that as 2x times dx dx if you want, but dx dx is 1. And the right-hand side is 0. So if I wanted to find this tangent line, right, if that was my goal, all I really needed was dy dx to do that. I can now solve this algebra equation for dy dx. So I get 2y dy dx equals negative 2x. And then I can divide over by the 2y. And I get dy dx equals negative 2x over 2y. And you can cancel the 2's. And you get dy dx equals negative x over y. So if we wanted to know the slope of that tangent line, I would just have to find the point here. And then take the x value and divide by the y value. Good stuff, right? So if we want to take a particular point here, if we wanted to do this, if I wanted to say that this point right here was root 3 over 2 comma 1/2, which is a point we know is on the unit circle there, then I could say that the slope of that tangent line so the slope of my tangent line would be equal to negative x over y. Well, what's the x there? It's root 3 over 2 divided by the y, 1/2. And this is just negative square root of 3. So let me come back here for a second. You can see what I changed. I just scratched out the a and wrote root 3 over 2 to give myself a particular number. That means that the point on the circle here is root 3 over 2 comma 1/2. It's the unit circle. So if I want to find this tangent line, if that's my goal, now that I have dy dx, I can find the slope of my tangent line by plugging in the x and the y. So our tangent line we have to use the point slope formula. It's y minus y0. That's y minus root 3 over 2 equals m, which is negative square root of 3 times x minus 1/2. That would be our tangent line. There's a lot of other things that this is useful for, but the kind of main idea here is that even if you don't have a nice function, you don't have something like f of x equals blah, 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 where it's all just x's. If you have some implicit expression involving both y's and x's, you can still differentiate through these. That's the big thing here for us as calculus students. Even if you don't have an explicit formula like y equals f of x, even if you have some messy formula that involves both y's and x's on both sides, you can still differentiate through those. It's just that every time you bump into a y, you have to kind of treat it like a chain rule thing. You have to remember that y is actually secretly a function of x. It's not its own variable. Y is implicitly determined by x. which means that when you dig all the way in here and you differentiate with them, you need to think about the y's as a chain rule thing. After differentiating the outside, after differentiating like normal, you have to multiply by dy dx. So I'll show you some more examples. First, I'd like to take any questions on the actual mathematics that we did here.
Yeah, I have a cool question. So I just want to clarify. So we put dy dx when it has to do with y, and then dx when it has to do with x.
Well, you don't have to write the dx dx. Nobody would write that, right? It's just that the derivative of x squared when taken with respect to x is 2x, right? This is the normal derivative that we've always seen. And what I'm saying is that you can understand that in this context by thinking of it as though there is a dx dx there. It's just that dx dx is 1. How does x change as x changes? All right, well, x, you know, am I saying this right? X is the independent variable and y is the dependent variable. So y changes when x changes. We think of y as depending on x, and we think of x as being able to move freely. So the derivative of x squared is our normal derivative of x squared is 2x. The derivative of y squared, I cannot think of as just following the normal derivative rules because the inside piece here actually changes when x changes. And this derivative, d dx, measures the change of this whole thing as x changes.
Okay.
Does that really help? I'm sorry, I'm trying to get at what.
Yeah. I mean, I'm just like seeing how, I mean, d over dx wouldn't have changed our final answer anyways. Like if we didn't put that, we would have still got a negative x over y. You know what I mean?
Well, if you wrote d dy here instead of d dx, then you would be taking a different kind of derivative and you would get a different answer.
Would that ever happen?
Sure. Oh, yeah. Yep. Yeah. When we talk about implicit differentiation, especially when we start talking about related rates, we'll be differentiating with respect to time. We'll be differentiating with respect to all sorts of things. It will not always be one of these two variables. And sometimes it'll be one or the other. We can talk about all sorts of derivatives. So x will not always be the independent variable. But in these early examples, that's how I will treat it because I know that's what we're most used to.
Okay. Thank you.
Sure. Of course. Fabrice asks, where did the 1/2 come from? So up here, I'm just using what I know about the unit circle, right? I know that the point on the unit circle where the x value is √3/2 has y value 1/2. I'm thinking of this being as the point associated with 30 degrees or pi/6. So I had to pick some x value for a, and then the y value that I put here happens to be the one that I know is on the unit circle with this x value. So kind of imagine that the picture was just given to you like this at the start. This is some knowledge that we have a priori. It's not something that I like solved for, although you could solve for it if you wanted by plugging √3/2 in here and then solving for y. But this is just a point that I know is on the unit circle in the first quadrant. So I chose to label this point with these coordinates so that I could do an explicit example. And then Joe is asking, what happened after negative x over y? So down here, we figured out that our derivative dy dx is equal to negative x over y. And remember, dy dx, that's the same as f primed, right? That's what gives me the slope of the tangent line. It's just that here I don't have a function f, so I can't call it f primed. We just call it dy dx, or sometimes we'll call it y primed. But the idea is that this thing I know gives the slope of the tangent line, right? F primed is the slope of the tangent line. So if I want to find the slope of the tangent line and I have dy dx, I just have to plug in the x's and y's that I need here. I just need to get the number out of this that is associated with that point on the curve. So what I wanted to do is find the slope of the tangent line at this point on the curve. At this point on the curve, x is √3/2 and y is 1/2. So if this is a formula that tells me the slope of the tangent line at the point x comma y, and I want the slope of the tangent line at this point, then I have to plug in this for x and this for y. And that's exactly what we did in the next line. So that's what we did after negative x over y.
Okay, that makes sense.
Cool.
So then the form on the right underneath, so our tangent line is, what form is that for the?
This is point slope.
Okay.
Y minus y0 equals m times x minus x0. This is the point slope form of the line. The point there is 1/2 comma root 3 over 2, and the slope is negative root 3.
Okay, thank you.
Of course. Okay, let me show you some other stuff that we can do with this. This is kind of why it's nice to do an intro day for these things, right? This fits beautifully into our schedule because these concepts are a little bit tough to wrap your head around at first. So I'm glad we have a low pressure introduction day here. There are some functions we don't know how to differentiate yet. Right? We might think that we know how to differentiate all the things now that we know all the rules, but we really don't. Natural log of x, the inverse tangent of x, or the inverse, what was I going to do? I was going to say inverse sine of x, inverse cos of x, all the inverse trig. All right, these are things we have no idea what their derivatives are right now, right? What is common among these functions that I've listed here? What do these all have to do with each other? I mean, the bottom three are definitely all inverse trig functions. What do those inverse trig functions have to do with the natural log function?
Isn't that the inverse of a log?
Yeah, exactly. These are all inverses of other functions. So, note, these are all inverses of known functions. And so the kind of trick that we're going to use to get the derivatives here is this inverse function theorem. Now, I'm not going to give you the inverse function theorem as a theorem. It's not overwhelmingly difficult. It is a part of this class when we teach this class at UF, but it's not an official part of the class here at Santa Fe, and we can do all the things with it without actually, calling it by its name. But I just want to tell you that the thing that's going on in the background here is the inverse function theorem. The Wikipedia page is reasonably digestible if you want to take a look at it. But kind of the trick here is to use implicit differentiation. So to get these derivatives, and any like them, we use implicit differentiation. Let's start with y equals ln x. According to the definition of the natural log, y equals ln x is the same as saying e to the y is equal to x. All right, that's what we mean when we say that this is the inverse of this. All right, that the natural log is the inverse of the exponential. And now, if I apply d dx to both sides, I get this. And d dx of e to the y, well, that should be e to the y times dy dx, right? It's just the normal chain rule. It's just that we have to remember y is a function of x. This is that same implicit differentiation thing. And then on the right-hand side, the derivative of x is 1. You can think of 1 times dx dx, but dx dx is also 1. It doesn't give you anything new. Now, what is e to the y? But e to the y is x. So this becomes x times dy dx equals 1, which means dy dx is 1 over x. So if y is the natural log of x, then dy dx is 1 over x. In other words, the derivative d dx of natural log x is 1 over x. And this certainly is a true statement. The derivative of ln x absolutely is 1 over x, and this is how we prove it. We begin by rewriting this explicit formula as an implicit formula. This is called an implicit formula because it's not solved for y, right? Rather than having y equals some stuff, I have an expression that involves functions of y and functions of x. And then I differentiate implicitly on both sides with respect to the variable x, because my goal is to get dy dx. I want to know what's the derivative of ln x. The left-hand side here, I use the chain rule. The derivative of e to the y should be e to the y, but since I have, y as a function of x, y is not just the variable x, I have to multiply by the derivative of the inner function. And the derivative of x is just 1. Now, according to my definition, e to the y is the same as x, right? That's the line we had just above the derivatives here. That's this. E to the y and x are the same. So I can swap that e to the y back to an x, and I get x times dy dx equals 1, which means dy dx has to be 1 over x. Just divide both sides by x. So if y is ln x, then dy dx is 1 over x. In other words, the derivative of ln x is 1 over x. That's the statement. This is just a little taste of what we can do with implicit differentiation. I don't want to overwhelm with this, so I'm going to show you the inverse tangent function. Look at your textbook, see if there's anything else that I want to say while we're here. But then I think I'll probably let you guys go. You guys have had a challenging few days. I don't think there's much else that I want to really bludgeon you with right now. Implicit differentiation, logs. Yeah. So here's what they're talking about, where you just look at like one piece at a time, right? And those one pieces we can handle. And here's just lots of examples with implicit differentiation. We'll get to that. I don't want to scare you with any of this too much. They should be doing inverse trig stuff here. Yeah, okay. So this is the last thing I'll do. I'll give you one example of an inverse trig derivative right now, and then I'll let it kind of steep in your brain over the weekend. And on Monday, when we come back, I'll finish with the remaining inverse trig derivatives, and we'll dig into this section in earnest. So that's our last little bit for today. After this, you guys can go. Let's find the derivative of the inverse tangent function. This is the nicest one. Think about what we just did with the natural log function. We're going to start with y equals the inverse tangent of x and try to get dy dx. That's our goal. If y is equal to the inverse tangent of x, then what is the tangent of y equal to? This is equivalent to what statement that starts like this?
Wouldn't it be just equal to x?
Yeah, exactly. That's what it means to say that this is the inverse of the tangent function, right? There are some domain restrictions that come along with the inverse tangent function. I'm not going to worry about that right now. It's not important for this, but you could say that this implies this only if y is between negative pi over 2 and pi over 2, but it's irrelevant for what we're going to do. All right. So when we did the log function, we started with y equals ln x, and then we said, okay, that's the same as e to the y equals x. What did we do after that? We took a derivative, right? I'm sorry, go ahead.
Oh, I just said differentiate.
Yeah, exactly. So I'll apply the operator d dx to both sides here. So I'll differentiate on both sides with respect to the variable x. The right-hand side is 1. The derivative d dx of x is 1. What's the derivative of the tangent function?
Secant squared.
Good. So this will be secant squared of y times dy dx. All right, differentiating the outer function, derivative of tangent is secant squared. I leave the inside alone. And then we multiply by the derivative of the inner function. The inner function is y, so its derivative is just dy dx, or y prime. So you see, implicit differentiation really is just the chain rule. There's nothing magic going on here. It's literally just the chain rule. But now, I want to solve for dy dx. And I'd like to rewrite secant squared of y in terms of x's. Off to the side, I'd say, now we know that tangent squared of y plus 1 is equal to secant squared of y. This is the Pythagorean identity. All right, it's a trig identity. Tan squared plus 1 equals secant squared. So what we really have here, secant squared is the same as tangent squared plus 1. So secant squared of y is tangent squared of y plus 1. And then I still have my dy dx here, and I still have my 1 over there. But tangent of y is x. So tan squared y plus 1, this is the same as x squared plus 1. And then if you divide over by this term, you'll get dy dx equals 1 divided by x squared plus 1. And that is the result. The derivative of the inverse tangent function of the inverse tangent of x is 1 over x squared plus 1. And the other inverse trig derivatives we will cook up in the same way. This trick using implicit differentiation. The other things we're going to do, big things we're going to do with implicit differentiation is solve general tangent line problems where, you know, you've got a mess of y's into x's. And then we're also going to learn how to solve some related rates problems, which are a lot of fun, like figuring out if I'm pumping, you know, air into a balloon at this speed, how fast is the balloon blowing up? You know, all of those sort of fun things. This is where I'll leave you guys for today. Like I said, don't want to dump too much on you. You did good on the test. I want to just let you relax and breathe over the weekend. Do think about the concepts here today. And if you have time, I invite you to read the Wikipedia pages on the inverse function theorem and the implicit function theorem. These are both really beautiful things. And also take a look at your textbook. Take a look at the section on implicit differentiation, because this is where we're going when we come back on Monday. I'm not going to give you any fresh homework. All right, you're safe over the weekend, but please take this time to catch up. If there's anything that you didn't get done before test one, this is a really good opportunity to get that shit done. When we come back, implicit differentiations, derivatives of log functions, these are really the same thing. Then we're going to do related rates, linear approximation, and then we're going to start talking about min and max problems. I think probably we'll do everything up through related rates next week, and then we'll start on chapter 4 the following week. Any questions for me before I let you guys go?
Can I ask you a question about the test, like one of the questions from it?
Sure.
So this one's like really been bugging me. It was x cubed minus 27x plus whatever number, I don't know. And then you asked us if the tangent line had any horizontal asymptotes. So since it was the x cubed, the original x cubed function is like a snake that passes through the origin and then finishes. So it's like it goes down as it's approaching to the left, it goes to negative infinity. As approaching right, it goes to positive infinity.
Mm-hmm.
So since that whole entire function is increasing the entire time, I was thinking that it will never go below the x-axis, and I was thinking it would be the horizontal asymptote x is equal to 0.
Let me make sure I'm following the problem you were talking about. So we're not asking about horizontal asymptotes. We're talking about horizontal tangent lines, right? Those are very different questions.
Ah,
We're looking to find any x values where this thing has horizontal tangent lines. And the fastest way I can answer this is with a quick Desmos graph. So x cubed minus 27x minus 3.
okay. I guess I just read the problem wrong.
That's frustrating. I'm sorry. The derivative here is a polynomial, so it wouldn't have any asymptotes at all. But this thing does. If I rescale my y-axis here, sorry. Let's see, 200. This thing does have some horizontal tangent lines though, right? So if I'm marching along here, when I get to this point right up here, right at the top there, I have a horizontal tangent. And right at the bottom here, I have a horizontal tangent.
Wait, could you share the screen really quick?
Oh, sorry. Yeah, I didn't realize I had it off. Yeah.
Thank you.
Yeah, so a little Desmos graph will help, right? A horizontal tangent line, that's like, you know, imagine you're like skiing along the graph. Where are your skis horizontal? Well, right as you go over the top of this hill, your tangent line would look like, right? It would be horizontal.
Mm-hmm.
And the same thing is true at the bottom of this valley. Right as you ski through the bottom of this valley for a brief second at the bottom here, your skis would be horizontal. So this does have horizontal tangent lines. There's two places. One of them is at -3, the other one is at +3. The way we find that is by taking the derivative and setting the derivative to 0. Remember, the derivative gives the slope of the tangent line. A horizontal line has slope 0. So where the derivative is equal to 0 is where we have horizontal tangents.
All right. Thank you.
Of course. Yeah. Any other burning questions about the test?
If we showed work on the multiple choice portion, but we got the wrong answer, but we did some of the work right, will we get some points back, or is that only the short answer?
Depends. My usual rule is there's no partial credit on true, false, or multiple choice. About once or twice per year, I make an exception where somebody like wrote out all the work for the multiple choice and did everything correct and clicked the right answer or whatever, circled the right answer, then erased it. And then sometimes I can be swayed to give some partial credit on there, but the general answer is no. General answer is if the multiple choice for true false is wrong, it's wrong. If it's right, it's right. But if there's a compelling argument that partial credit really is deserved there, then I will consider it. But for the most part, multiple choice and true false are just right or wrong. And then the free response, I'll give as much partial credit as I can.
Okay, thank you.
Professor,
Yeah.
could you go over the one where you were given like y is equal to something cubed plus something squared plus something, or sorry, it would be like x cubed something x squared plus x, and then you wanted to find when you change directions?
Yeah, so that's this guy, right? We want to know when does the particle change direction. This is actually very similar to that one. This is a position function. Particle is going to change direction when the velocity function changes sign. Let me write it down. S of t here is 2/3 t squared plus 13 halves. Oh, sorry, t squared. This is a t cubed plus 13 halves t squared plus 11t. All right, so when does this change direction? Well, if this is S, particle changes direction when the velocity function changes sign, right? When velocity goes from positive to negative or from negative to positive. Remember, if the velocity is positive, the particle is moving to the right. If the velocity is negative, the particle is moving to the left. So when the velocity goes from positive to negative or from negative to positive is when this particle will change direction. So you need to take the derivative of S of t to get V of t. The velocity is the derivative of the position. So if I differentiate 2/3 t cubed, I get 2t squared. If I differentiate 13 halves t squared, I get 13t. And if I differentiate 11t, I get 11. And now I need to factor this. So I need two numbers that multiply to 22 and add up to 13. 2 and 11, right? Yeah. So this is 2t squared plus 2t plus 11t plus 11, which is 2t times t plus 1 plus 11 times t plus 1. So this is 2t plus 11 times t plus 1. So v of t equals 0 at times t equals -1 and t equals, what's that, -11 halves, right? So your velocity function kind of looks like this. -11 halves is like -5.
Could you show the screen?
Oh yeah, yeah, I got you here. So position. We want to know when does the thing change direction. So that means we need to know when does the velocity function change sign, go from being positive to negative or whatever. Velocity is the derivative of position. So I take the derivative of this function and I get this, which I now aim to factor because I want to find out where it changes sign. So I factor this. And we discover that the velocity function looks something like this. So we're negative, positive, negative, positive. So the particle changes direction at times t equals -11 halves and t equals -1. Those would be two possible answers here. Yep. The big idea there that you need to remember is that the sign of the velocity gives the direction. If the velocity is positive, you're moving in one way. If the velocity is negative, you're moving in another way. So to figure out when the particle changes direction, you need to figure out when the velocity changes sign. Or in other words, you need to at least find where the velocity is 0. right? Because in order to change direction, you got to stop for a minute. Now, it's possible that there are solutions to v of t equals 0 where you don't change sign. But in this case, both of those solutions are places where you do change sign. So here, all you had to do is find the velocity function and then factor it. So that equals 0.
Okay, thank you.
Of course. Other burning questions here? All right, then I'll go ahead and let you guys go. Take the time, relax over the weekend. I'll get your exams graded as soon as I can, no later than next Wednesday. Get caught up on any homework that you haven't done yet. And then on Monday, we will meet to continue talking about implicit differentiation. Take care, guys.